So welcome back. Thanks, Angie. It's great to be back in London. It's great to be at Strata. Really great to see how the conference has evolved so much. Now, to get started, you've probably all been there. You've just finished some project which you hope had a positive impact on your business. And now the only thing that's sort of left to do is to evaluate whether your project was a success. Now that sounds easy, but in practice, if you think about it, it means you need to understand what actually happened and what would have happened if you had not run your project. And looking at the differences between what actually happened and what would have happened otherwise, that's exactly what puts your question right at the heart of causal inference. So causal inference is the branch of statistics that's concerned with the effects of our actions, with the consequences of what we do. And that's why causal inference is one of those key areas of data science. Because if you can manage to extract one causal law from your data, that can be more powerful than all the dozens and dozens of correlations you might find otherwise. So in this session, I'd like to focus on causal inference techniques that you can use in your daily work starting today. I'm Kai Brodersen. I'm a data scientist at Google, and the kind of techniques that I'd like to share with you today are things that we've been developing and using for a long time at Google. Especially for those of you whose main area of expertise is in areas other than causal inference, my goal for today is to make sure that each and every single one of you walks out, leaves this conference with a better intuition than before about how you can use causal inference in the strategic parts of your work. Okay, so let's jump right into an example. So 2.5 years ago, on the 15th of January in the early morning, the Swiss National Bank released a press release in which they declared that they would no longer support the peg, or the fixed exchange rate between the Swiss franc and the euro. Now, within minutes of that press release being published, the exchange rate between the two currencies, which had been rock solid for years, all of a sudden became subject to the free forces of the market. As a statistician in causal inference, what we'd like to ask is, what was the effect of publishing that press release? And the answer in this case is pretty easy, because everybody in this room would probably agree that this is what would have happened to the exchange rate if the press release had not been published. Okay. Now, in causal inference lingo, we're comparing the observed data y1 to what we think would have happened otherwise, a counterfactual. The counterfactual data, an estimate of the counterfactual y0. Sometimes people refer to this as a synthetic control. It's a useful term that's been popularized by Aberdeen and colleagues to indicate this idea that there is no experiment here. We don't have a control group, yet we want to create a control, an estimate of what we think would have happened. And creating that counterfactual is important because the causal effect that we're interested in is always the difference between those two, what actually happened and what would have happened. And as a nice rule of thumb, whenever you look at a time series chart, causal effects are always the vertical arrows. They never go across time, horizontally or diagonally. Now that's an easy one. In practice, though, our cases might look a bit more like this one here, where you've got some time series. This could be sales, clicks, conversions, anything of interest. And we did something at a certain point in time. Say you launched that marketing campaign, or you released that new feature, or you changed your terms and conditions. Something that you did to your business, and you want to figure out what would have happened had you not taken that action. You want to estimate that blue line. And in this session, we're going to focus on ways of doing that. Once you have that estimate, the difference between those two, that's going to be the causal effect of your action. And one of the things I'd like to convince you about in this session is that you can run this kind of analysis in no more than 3 lines of code. So we'll see how we get there. Let's take a step back, though, and remind ourselves what we're really dealing with in this area, in this field of causal inference. Causal inference starts with a treatment. There's 2 things we can do. We can either take the treatment, in which case we get to observe the potential outcome under the treatment, or we can choose not to take the treatment, in which case we get to observe the potential outcome under no treatment. Now, importantly, we can't do both of these things at the same time, which means we can only ever observe one of those two potential outcomes. And that's a problem because the causal effect of the treatment is the difference between those two potential outcomes. Since we can't observe both at the same time, we can never ever observe a causal effect. We can only hope to estimate it through clever data acquisition and statistical modeling. Perhaps with one exception, how many of you remember the 1985 trilogy Back to the Future? Let's have a quick show of hands. Everyone. For those of you born after 1985, I'll go a quick recap. What happens in Back to the Future is we are joining the actors in how they're taking a sports almanac from the future. That's, by the way, that was 2015, not quite so futuristic anymore. They take that sports almanac from 2015 back into the past, and that's a handy thing to have in the past. It allows you to bet and win just about every single time. Doing so turns Biff Tannen, who is originally this rather unsuccessful nobody, into an ultra-rich real estate tycoon, shown here depicted on top of Tannen Tower. So in that movie, we actually get to observe both of these potential outcomes, and that means we actually observe the causal effect of taking something back into the past. Now, in practice, we can't do that, and so we'll have to resort to statistics to solve this problem. If there's one thing you remember from this session, then let it be this slide here. And for those of you taking pictures, I'll let you know when the slide is complete, so it's easier. So whenever you have a causal inference problem, my advice is to start with a table that looks like this. Every row in this table represents a unit. For example, this could be a participant in a psychology experiment, or it could be a user in a web traffic experiment, or it could be a customer in a sales experiment. And the first thing we note down for each of these units is their treatment status. 1 for treatment group, 0 for control group. Just the standard setup. Let's say that the treatment was randomized. Now, what the table makes explicit is this idea that there are these two potential outcomes, not just the observed data, but we're thinking in terms of things that we could potentially observe. The first one is Y1, which we only observe for the treatment group. That's what happens under the treatment. And we'll never ever know what Y1 would have been for the control group, since they weren't treated. And the other one is the potential outcome under no treatment, which is something that we observe for the control group, but we'll never know what Y0 would have been for the treatment group, since the treatment group was treated. And then there are other variables. These are typically things that we record before the treatment starts, pre-period covariates, variables that describe units. They turn out to be very useful. I won't go into too much detail about those. Let's just for now say that we have other variables that we collected before the treatment started. Now, when you look at yourself or your colleagues analyzing a randomized experiment, typically you'll see people do something like this. You focus just on the observed outcomes, and you might run something like a t-test to compare your treatment group to control group, answer the question of whether there is a statistically significant difference, and that's the end of the analysis. So you'd infer your causal effect estimate from the observed outcomes. But it turns out there is often a statistically much more powerful approach, and that is by taking a detour and first estimating the missing potential outcomes explicitly. For example, using some sort of model, say a regression model. Once you have estimates of these missing potential outcomes, you can just read off your causal effect directly. It's almost like as if you had a complete data set where everything that could be observed is now either observed or estimated. In many cases, though, we don't have, I'll just quickly go back for those of you who'd like to take notes on this slide. This is like the classical case of a randomized experiment where things are easy. In practice, though, we often have situations where we don't have that luxury. Think of big events, big actions that your business might take. Running a campaign, changing a feature, releasing a new product version. All of these are the kind of things where you don't have an alternative version of your company sitting around that you could treat as a control group. Think of big political decisions, economic decisions. There is only one UK, there is only one Brexit decision. There isn't a control group where you can see what would have happened otherwise. These are all the kind of situations where our table looks rather more like this one here, where we sort of have one unit, that's us, that's our company or our country. The treatment has already happened. We know what happened under the treatment. What we want to understand is what would have happened without the treatment. So if we can find an estimate for that potential outcome under no treatment, then we can determine the treatment effect simply by comparing those two. Importantly, we don't want to just have a point estimate. We want to repeatedly estimate these missing potential outcomes. In a Bayesian context, you typically do this by sampling from the posterior distribution over your missing potential outcomes. And doing that repeatedly gives you samples from your causal effect estimate tau. You can then summarize these samples and, for example, report the posterior mean or a CI to indicate the uncertainty in your causal effect estimate. Okay, so that's going to be the general strategy that we'll use here. We're in the world of causal inference. We'd like to estimate causal effects. To do that, we need to estimate the missing potential outcomes, and once we've done that, we can infer our causal effects. Okay, so let's go back to our example and see how we can actually do this. This is the time series that I showed at the very beginning. And let's say that we did something to the market on the 1st of January 2012. Okay. Now that event splits our time series into two parts, the pre-period and the post-period. And that's really all we need to know, since the event that happened on that 1st of January could affect the time series for any time in the future. Now what we want to estimate is something like this, an estimate of the counterfactual. So the blue solid line here shows a point estimate, and the light shaded area represents a 95% credible interval. You can see how this interval represents our uncertainty, grows over time, it widens over time, corresponding to our intuition that the further you predict into the future, the more uncertain you should get. These are the kind of properties that we want to build into our models. Now you might ask, how on earth did we come up with such a specific prediction of what would have happened? What's this even based on? And the answer is that the most powerful ingredient of creating such predictions is to use other time series. Other time series which are related to our outcome variable, the black one, but which we know, or at least can safely assume, not to be affected by the treatment themselves. So here I'm showing two covariates, red and green. These could be, say, sales of some other product, queries for your competitor's brand, clicks on unrelated entities, things that are possibly related to your outcome variable, y, but which you know are not themselves affected by the thing that you did on the 1st of January. Given these kind of time series, these could be one or two or dozens or hundreds. The idea now is to simply say, let's split this whole problem into two parts. First of all, we're going to learn the relationship between how red and green explain black. And then in the second part, we're going to simply apply that learned relationship to predict what should have happened to the black time series given what red and green did in that post period. Okay, so that's the strategy how we can turn a causal inference problem into a model selection and prediction problem. Simply converted one problem into another. We're going to learn how the three time series are related in the pre-period, and then simply predict what should have happened to the black time series in the post-period, given that we already know what happened to red and green. Once we've done that, the difference between what actually happened to our outcome variable, black, and what we predicted should have happened, that's blue, that difference is going to be an estimate of our causal effect. So let me push that plot up to the top of the slide, and what I'm showing here at the bottom is that delta curve, the difference between the observed data and our counterfactual estimate. And that's our estimate of the causal effect of the action. Sort of, you can see how it's hovering around 0 in the pre-period. That's reassuring. We didn't have an effect on the past. And then it's shooting up, decaying back down to 0. I generated these data, which means we know the true causal effect, and that true effect is shown by the green solid line. So you can see how the model recovered accurately that true effect which we injected into the data. What kind of models could you use for this? In principle, this could be any model. We started out with simple regression models. We then moved on to Bayesian structural time series models, which is an extremely rich and powerful class of time series models on a Bayesian foundation. Currently, we're also experimenting with deep learning methods. The method that's implemented in CausalImpact, the library that I'll cover in a second, is the model that you see here on this slide. This is graphical model notation. It's a time series model that has all these different components simply stitched together. It's a component that describes the current level of the time series. There is a component that describes the current trend. And then there is a mechanism for placing a so-called spike and slab prior on the covariates. That's a way for us to automatically identify which covariates are useful in predicting our outcome variable. Just to give you a flavor of the kind of models you could use for this. In principle, it could be any kind of model. We've done most of our analyses using the kind of model that you see here, called Bayesian structural time series models. I'll show you one more example, and then I'd love to try a demo on my laptop. So here's an example from Google AdWords. You all know Google AdWords. It's the system that decides if a good answer to your query on google.com is to connect you with a business, it shows an ad. And the data I'm looking at here is data from an advertiser who ran an advertising campaign on google.com for 6 weeks. Our outcome variable is the number of clicks that this advertiser got to their website. And the counterfactual, of course, is how many clicks would this advertiser have gotten had they not run the advertising campaign. So the black curve is the number of actual clicks. The blue dotted line is our estimate. And the covariates that are used for this analysis are queries to this advertiser's competitors, other brands in the same market. These are amazing covariates which you can get for free using Google Trends. It's a great source for collecting these kind of other time series. Now, in this case, the advertiser actually ran a randomized experiment. And that's great news because it means we can now repeat the analysis and actually using the control group, the real control group, like the best way of getting causal inferences from this experiment. And when you do that, then you get this kind of picture. So the two plots are almost identical. They certainly give us the same kind of conclusions about the effectiveness of this advertising campaign. This means that the bottom plot is based on a randomized experiment where you've held out half of your market from your campaign. The top plot doesn't need that. You can target your entire market. Yet you arrive at the same conclusion, showing the potential that synthetic control methods have. There's a lot of documentation. For those of you who'd like to read more about this, there's a paper that goes a lot more into the theory of how the method works. And what I'd like to focus on more in this session here is a quick demo. So everything that you saw so far is implemented in an R library called CausalImpact. And we open sourced this library recently. So I'd like to give you a quick overview of what the library does. Okay, so I've got a little toy data set here. Very simple data set. It's got 100 observations and 2 variables. Y is our outcome variable, and x1 is our single covariate. I've seen a lot of analyses in the wild that use just one covariate. In practice, you want to use at least a handful or even dozens of covariates just to get a richer model. Let's take a quick look at these data. Okay, so this is what we have. The black line here is our outcome variable, and the red dotted line is our single covariate. Okay. You can already see how the two are correlated. It's a super simple toy example. Things are nice and easy. We did something to that system at time point 71. And so our question now for this method is, what do we think would have happened to that black time series after time point 71, given what we know happened to the red dotted line? And sort of just by squinting, looking at this time, everybody can probably estimate that the black time series wouldn't have shot up quite as much. It would have meandered slightly down, given how the two are correlated. Now, the simplest possible type of analysis I can run by just specifying one more thing, the pre-period, which goes from time points 1 through 70, and the post-period, which is from time points 71 through 100. That's all I need to specify for this simple kind of analysis. What's happening now in the background is the graphical model that you saw on the previous slide. We're drawing posterior samples from that model, building a model based on the pre-period, then using that model to predict what should have happened in the post-period, sampling from it, and getting a posterior distribution over our causal effect. So let's take a look at this object. This is a ggplot object, so I can work with this in the usual ggplot way. Okay, so there are three panels here. The top one shows the original data in black and a counterfactual estimate as a blue dotted line with 95% credible intervals around it. You can see, sort of as expected, our synthetic control says the time series wouldn't have shot up as much. It would have stayed at a slightly lower level after time point 71. The second panel shows the delta between the two, telling us that we have a causal effect of around 10 every time point. And the third panel simply adds up these individual daily causal effects over time. So across that period, we end up with a total causal effect of around 300. Looking at the actual numbers, I can just take a look at a summary of the posterior inferences here. So this, for example, tells us that the observed data had an average value of 117 in that post period, but we would have expected a value of only 107. And so the difference between those two is our causal effect estimate, our average causal effect in absolute terms and in relative terms. And the analysis tells us that we are supremely confident that there indeed was a causal effect in our data. If our covariates weren't rich enough, or if our covariates weren't at all predictive of our time series, then this analysis would probably tell us we don't know. There might be a causal effect, but we're not 99.9% certain, which can often be just as useful insight. Suppose you ran an advertising campaign and your analysis told you that there was absolutely no effect. You can take your budget, put it somewhere else. So null results in this sense can be just as useful as positive results. And finally, for those of you who have a healthy disregard to writing up the results of your analysis, like writing up the kind of usual reports, once you've done that a few times, you kind of get bored of it. So the package has a function that's part of it, which describes what your data was, what your model was, what results you found, and what they mean. You can copy and paste that into whatever you like. There's no copyright whatsoever here. Okay, let me quickly thank the many colleagues and friends who've been contributing to this work over the years. in particular Steve Scott, who is the author of the BSTS library that implements the kind of Bayesian structural time series models that you saw, Alain Hauser, who is the current maintainer of the package, as well as Lars, Nicola, Penny, Fabian, Simon, Rowan, and Hal. And finally, amazing audience, let me thank you for your attendance and attention. Thank you. Okay, we have a couple of minutes for questions.
Right. So it was a while ago, maybe about a year ago, I got asked to estimate causal effects between collect a set of time series, quite a big set. Maybe it was like not very big, maybe 100. So the kind of question in the business side was, there's a trend here, it's in this geographical region, tell me, could it cause the trend to blow up a few months down the line there, right? And so I dug into this problem, then I did found out about Granger causality, partial Granger causality, dynamic Bayesian networks. I looked into all of this stuff. In this case, in this situation, there's no control, there's no period, right? So there's no intervention. You just want to find out the causal relation. And I was just basically surprised how difficult this problem was for more than a couple of time series, and how little documentation and kind of like work has done, except from some like people in bioinformatics looking at brain signals, etc. So do you think there's going to be a movement towards creating such packages in the future? Like you guys might create one, or what do you reckon?
Okay.
Sorry, long question.
So the question is, suppose you had multiple time series and you want to understand the causal structure between them.
Without an intervention.
Without a specific intervention. So this is a whole subfield of causal inference by itself, identifying the causal graph from the data. It's unrelated to this situation that we're looking at here. Here we have a specific event, and we want to understand the effect of that event. I can point you to a bunch of sources. Perhaps you already know the literature. There's a huge literature on identifying the causal structure from a set of time series.
Okay, thanks.
Hi. I'm glad you drew the biology comparison, because that's an important one. And we know when we run those experiments that we don't just not treat. We treat with something that's as identical to the thing that we're giving the patients, except for one covariate. So we give them a placebo. Because we know that doing stuff always has an effect. And we're interested not just in doing something, but we want to know in the difference between the thing that we're doing versus just doing stuff. So I just wondered if you had any thoughts on that, because obviously that's not catered for at this point in something like causal impact. You do something, it's going to have an effect.
Right. It's a great question. In any real treatment, there's always lots of things that you did. Even take a real business example of, say, releasing a new device and seeing what effect that has, releasing a new product, releasing a new pricing strategy. The important thing to keep in mind is that your interpretation hinges on your control set. So whatever is captured in your covariates is going to be your baseline. Some of the most well-known examples of this kind of approach, not in a Bayesian setting, but sort of in earlier times when models were simpler, are to actually look at policies and ask things like, Congress passed a new bill. What was the effect of that bill on the economy? Now, there isn't really a perfect control, but you can use a whole set of other countries and see how well they explain your country of interest in the past, and then use that same approach. And of course, in this case, the only option you have is to say any difference between what I observed and what I had expected, I can only attribute to the treatment.
Right, so we're a bit short of time. Kai and the other speakers would be available just after the talks, and you could come and ask questions then. So thank you, Kai.
Thank you.